Hello everyone. In our system design courses, today's topic is CAP theorem. Let's work on it. Let's understand it. What is CAP theorem? So, the CAP theorem, introduced by Eric Brewer in 2000, provides a fundamental framework for understanding the trade-offs that must be made when designing distributed systems. Okay, CAP theorem is introduced by Eric Brewer in 2000. Provides, what is this theorem provides? It provides a fundamental framework. It provides a fundamental framework for understanding the trade-offs. That must be made when designing the distributed systems. So basically here trade-offs means pros and cons. So while designing a system, we should aware what are the trade-offs. Suppose if you choose one database, a few pros will be there and also few cons will be there. And if you choose some other database, suppose SQL and NoSQL. Suppose if you choose SQL, it has its own pros and cons. NoSQL, it has its own pros and cons. And if you want to go with SQL, that means you are okay with the trade-off. That means that you are okay with the cons by NoSQL. So if we choose to decide at any point in the system design, you should take trade-offs as consideration. We should understand what are the trade-offs. Okay, what will be there. So we need to explain to the clients or the interviewer that okay, if we choose this SQL, this will happen and this will be work more. And if you choose NoSQL, this will happen. These are the cons, this will happen. So you should take the requirement and based on that you should proceed on these things. And the same thing Eric Brewer is proposed this CAP theorem. This CAP theorem will help us to handle this trade-off, to understand this trade-off while designing. So this theorem means C for consistency, A for availability, and P for partition tolerance. So this theorem will help us in understanding the trade-offs, that means choosing the trade-offs. CAP stands for consistency, availability, and partition tolerance, and the theorem states it is impossible for a distributed data store to simultaneously provide all three guarantees. That means any website or any application, it is impossible to provide all these guarantees. That means if it has consistency, maybe availability won't be there. If it has availability, consistency will be lacked. If it has both, partition tolerance may not be there. If all will be there, that's fine, but it is almost impossible to have all the three things: consistency, availability, and partition tolerance. So what is consistency? Every read receives the most recent write or an error. Consistency means if this application works today, day 1 and day 2 also it should work the same, day 3 also it should work the same. Or if it is any issue, it should throw an error. That is a consistency. It shouldn't change its actual behavior. And then availability. Every request, read or write, receives a non-error response without guarantee that it contains the most recent write. It means every request receives a non-error response. The availability, it should be available at any time, a point of time, it should be available. That means it will give some response. You do not know it is the most recent write. That means it is a consistent data. So here we should understand few terminologies. That means every read, maybe read we can say as request, write we can say as response. Write we can say like something else, but read means a request. Suppose every read, submit means every request receives the most recent write. Data should be consistent over every platform. So user 1 opened one system, user 2 opened another system. Your data should be consistent over every system. Your application should work like that. That means That means what should happen? Your that means it should take the most recent or updated value across the systems. Should be consistent. And availability, that means if you make any request, it should always be available. That means some non-error response, maybe it is not a recent, but before the recent may be available, but it not be the recent, that is availability. Partition tolerance, the system continues to operate despite an arbitrary number of messages being dropped or delayed by the network containing nodes. Okay, let's understand this definition. The system continues to operate despite an arbitrary number of messages dropped or delayed by the network nodes. Suppose if this is a network, how the network works is, if this is a network, this is a client, this is server. Server sends message to client. This system should operate, this should continue even if it is missing in between. That is called partition tolerance. Okay. In this article, we will explore the 3 pillars of CAP theorem, trade-offs, and practical design strategies for building resilient and scalable distributed systems. Okay, this CAP theorem will help us in trade-offs and also for scalability. So, first of all, the trade-offs, what we told, pros and cons, right? That means we should compromise either on consistency or availability or partition tolerance in any of these things. So let's check each of them in deeper and also understand the trade-offs. 3 pillars of CAP, that is consistency. Consistency ensures that every read receives the most recent write or an error. This means all working nodes in a distributed system will return the same data. The same thing we explained. Okay, user 1 will receive the same, user 2 also should receive the same. That is called the consistency. Here there are every read receives the most recent write. Okay, it will axis same. Or if there is no data, you should throw an error. This is called consistency. In consistent distributed system, if you write data to node A read operation from node B will immediately reflect the write operation on node A. If you write data to node A read operation from node B will immediately reflect the write operation on node A. Okay, that means suppose there are 2 nodes. This is node A and this is node B. Okay, if something user writes something into the server, that means it has most recent, then this B will immediately trigger. It will immediately reflect whatever this write operation is there will be copied here. Consistency is crucial for applications where having the most up-to-date data is crucial, like financial systems, balance query, like the bank systems. You should give the latest balance check and it should not be the old one. Okay. So in the banking systems, consistency is very important. Most up to date. And next, availability. And what we know about the availability, it should be up and running. Every time. Guarantees every request, read or write receives a response without ensuring that it contains the most recent write. That we already understand. It will receive a response for sure. For sure. This means that the system remains operational and responsive. Both will happen, even if the response from some of the nodes don't reflect the most up to date. So if you see, all nodes are same. User 1, user 2 and user 3 and user 4 requested. You returned X for both two users, but you returned Y for user 3 and you returned Z for user 4. That means system is available even though it is showing some incorrect data or inconsistent data. System is always available. That should be there. Okay, suppose where we can have this, such as online retail systems. Okay, that means if you are shopping at an e-commerce website, it should available all the time, even if it has suppose out of stock products. You go up to checkout flow, and while checking out it is out of stock, not a problem, but it should be available. Next, partition tolerance. What we understood earlier. Okay, about the network, partition tolerance is all about the network. Okay, partition tolerance means the system continues to function despite, that means available despite network partitions where nodes cannot communicate with each other. Partition tolerance means you should blindly understand it is a network drop. Okay, network drop. Suppose there are like 4 servers, S1, S2, S3 and S4. There are like 4 server nodes. System continues to work despite failure in communication. That means even if this fails, communication will still run. A network partition occurs when a network failure causes a distributed system to split into 2 or more groups of nodes that cannot communicate with each other. Okay, why this network should be partitioned? This will occur when network failure causes a distributed system to split into 2 or more groups of nodes that cannot communicate with each other. Suppose there in a distributed system, this is one system and this is another system. Suppose this is a network. If you are failed to have this, then you should have some other kind of network strategy. This is one network and from here it may go. So if this is failed, this will work fine. When there is network partition, the system must choose between consistency and availability. Okay, suppose network partition is there, then system should there is a trade-off then. If there is network partition, what is the trade-off? Trade-off is either you can choose availability. That means website will be available but data is not consistent. That means during the network problem. And consistency and availability cannot be achieved together. So you can choose either availability or consistency. Next, the cap trade-off, choosing 2 out of 3. Okay, that means we have 3, C, A, P. You can choose either these two, or either these two. The cap theorem asserts that in presence of a network partition, a distributed system must choose between consistency and availability. Okay, we already learned that if there is a network partition, that means there is a network failure, the distributed system will be split into 2 or more groups of nodes. This is distributed system 1 and another distributed system 2. It will be splitted. So if they cannot communicate with each other, so network partition will come. CP. Let's explore these scenarios. So if you choose partition tolerance and consistency, then what? These systems prioritize consistency and can tolerate network partitions, but at the cost of availability. That means this system may not be available, but you have the consistent data and you have the tolerant network partition. There won't be any network failures. During a partition, the system may reject some requests to maintain consistency. So if a failure happens, then only this network partition will happen. So at that time, if it is failed, it is rejecting some obviously it is rejecting some requests. That means it is losing availability, so it is unavailable. Okay, but it is consistent. Traditional relational databases such as MySQL and PostgreSQL, when configured for strong consistency, prioritize consistency over availability during network partitions. Okay, so databases, MySQL. So how MySQL is working? MySQL always have the consistent data. There won't be data problem. But it may not be available. Maybe database is down, server is down, or network is down, but data is consistent. Banking systems. Typically, banking systems prioritize consistency over availability. So all the banking systems, the website may not be available, but it is consistent. Since data accuracy is more crucial than availability. So here the trade-off is consistency. Consider a ATM network for a bank. When you withdraw money, the system must ensure that your balance is updated accurately across all nodes. Consistency to prevent overdrafts or other errors. Let's take the example of ATM. If you deposit or withdraw in an ATM, it should update immediately to all nodes to have the updated balance in your account. Suppose if you take availability over consistency, if this update is not happened in any nodes, you will have balance mismatch. You can credit or debit incorrectly, but you will always have this access. But this is not important, this is important. So consistency is important here. Next, AP. How we can have availability and partition tolerance together. Suppose these systems ensure availability and can tolerate network partitions, but at the cost of consistency. During a partition, different nodes may return different values for the same data. So NoSQL, obviously availability means no reason data. NoSQL databases like Cassandra and DynamoDB. So DynamoDB and Cassandra are examples of a AP, availability and partition tolerance kind of things, and NoSQL databases designed to be highly available and partition tolerant, potentially at the cost of strong consistency. Okay, suppose this DynamoDB, Amazon's DynamoDB, how it is working, it will never fail, but data is inaccurate. We can have this kind of scenario in some use cases. So at that time, this availability and partition tolerance is fine. That means if a network failure happens, data is inconsistent but system is always available. So Amazon's shopping cart system is designed to always accept items, prioritizing availability. When you add items to your Amazon cart, the action almost never fails, even during high traffic periods like Black Friday. That means even it has huge traffic, Amazon shopping cart system should always accept the items. That means if you click on add to cart, to it is not necessary to have consistency in this part, in this particular feature. It should be available. User should always be allowed to add the item to the cart. Consistency and availability. Okay, next our group is consistency and availability. Now how can we achieve both of them in the cost of network partition? Can be both. Suppose if there is no network partitions, then we can achieve consistency and availability. However, network partitions are inevitable in distributed systems, making this combination impractical. As we already earlier discussed, network fails are very common. At any point of time, network fails can happen. So, but if we consider there is no network fail, then we can achieve consistency and availability. Example, single node databases can provide both consistency and availability but aren't partition tolerant. In a distributed setting, this combination is theoretically impossible. So in distributed system, there is no chance of having both combinedly, but in a single node we have that. Next, practical design strategies. Let's check some design strategies. Designing distributed systems. If you want to design a distributed system, requires carefully balancing trade-offs based on application requirements. Until then, we understood what are the trade-offs, like CAP. Based on the CAP theorem, we observed like CP combination, AP combination and CA combination, all the three combinations. So let's understand the strategies. While designing a system, how we can carefully balance these trade-offs. That means if in CP availability is a trade-off, so how can we balance that? Okay, here are some practical strategies. Eventual consistency. What is eventual consistency? For many systems, consistency isn't always necessary. Eventual consistency can provide a good balance where updates are propagated to all nodes eventually but not immediately. That means like asynchronically. System where immediate consistency is not crucial, such as DNS and content delivery networks. Okay, what is eventual consistency? Eventual consistency means if it is system is always available and also it is partition tolerant, both are happening, but you want consistency also, then you can apply the strategy eventual consistency. That means it is not immediately consistent, but it will take some time eventually. That means after some delay it will happen. For that, the example is CDN, content delivery network. What this content delivery network will do? This will actually this will serve the assets, some static assets from the recent nodes. Suppose there are network of nodes, node 1 and node 2 and node 3. Okay, there are like three nodes. User 1, user 2 and user 3. So each user will access their nearest data center. Okay, suppose if our system is trade-off is consistency, maybe our N3 is not consistent, but it will eventually it may update, and user 1 will have that in their bucket. Strong consistency. A model ensuring that once a write is confirmed, any subsequent reads will return that value. Practical strategies in this eventual consistency, and in strong consistency, obviously ATM is the best example. Next, tunable consistency. What is tunable? Tunable consistency allows systems to adjust their consistency levels based on specific needs. providing a balance between strong and eventual consistency. Systems like Cassandra allow configuring the level of consistency on a per query basis, providing flexibility. Applications needing different consistency levels for different operations, such as e-commerce platforms where order processing requires strong consistency, product recommendations can tolerate eventual consistency. Okay, you understand what is tunable. Tunable means based on the requirement or based on the feature we can tune our consistency. Either it can be strong or eventual. Okay, based on the specific needs. What are the needs? So in a e-commerce platform, suppose for order processing, it should be consistent for sure, strong. But if you search for a product, there it won't be much problem if it is not consistent. Eventually consistent. Next, quorum based approaches. Quorum based approaches use voting among a group of nodes to ensure a certain level of consistency and fault tolerance. Group of nodes to nodes means servers also. Ensure a certain level of consistency and fault tolerance. Example, systems needing a balance between consistency and availability, often used in consensus algorithms like Paxos and Raft. Okay, I think it is mostly an advanced one which is to explain more, but let's understand a bit more. Systems needing a balance between CA, that means both consistency and availability. In general it is impractical, but even if we want, at that time this quorum based approach is used. That means we vote among group of servers which is having best consistency or like that. Beyond cap. So we understood like three things will affect the trade-offs. What are the other trade-offs? Other factors that will understand as the trade-offs. PAC, ELC. What is this? While cap is foundational, it doesn't cover all scenarios, obviously. Daniel Abadi proposed the PAC-ELC theorem as an extension by introducing latency and consistency as additional attributes of distributed systems. So latency and consistency is one more attribute. If there is a partition P, the trade-off is between availability and consistency. Obviously, if there is a partition, then trade-off will be A and C. Else, the trade-off is between latency and consistency. Okay. This theorem acknowledges that even when the system is running normally, there is a trade-off between latency and consistency. In conclusion, the cap theorem is a powerful tool for understanding the inherent trade-offs in distributed system design. It's not about choosing the best property, but rather about making informed decisions based on the specific needs of your application. By carefully evaluating the cap trade-offs, you can architect robust and resilient systems that deliver the right balance of consistency, availability, and partition tolerance. Okay, so whenever whenever the topic is about the trade-off, so every system has its own trade-offs, right? So based on that, what is your trade-off? Okay, your data should always be available, or your data should always be consistent, or is it always partition tolerance? Based on that, we should compromise others. Suppose if it is partition tolerance, we should compromise either availability or consistency, and such that you can achieve partition tolerance along with availability or consistency. That is about the cap theorem. And one more thing is that PAC ELC, which is if you are able to achieve both consistency and availability, then latency will come. Okay, alpha latency. let's understand the complete CAP algorithm one more time. So CAP algorithm is introduced by Ethic. It is very fundamental while designing a distributed system, obviously. So consistency, availability, and partition tolerance. Consistency means data should be updated. Availability means it is updated but it is available but data is not consistent. Partition tolerance, that means if a network failure is happening, then how our distributed system is handling that. Okay, next, these all things we understood. There is network talk. Then how we can choose 2 out of 3. We should choose either 2 out of 3. We can choose consistency and partition tolerance, where we use in ATM systems, and availability and partition tolerance, like shopping cart, add to cart system. And consistency and availability, mostly impractical but single node services. So we understood how can we choose, what is CAP theorem and how we can choose the trade-offs. Now, what are the strategies? Suppose you are able to achieve partition tolerance plus availability, then you also want consistency. Then you can go either for eventual consistency, that means it is not up to date, but after some delay it will get. Then strong consistency. How can we achieve strong consistency? You should compromise availability for sure. And then while designing, these are the practical strategies we should think of. Where can we go with eventual or strong or tunable? If it is tunable, based on the feature or the needs, we can tune our consistency. Theorem based approach. Thanks for watching the video. Hope you understand what is the CAP theorem and how can we use that while designing a system, distributed system.